Hello there. I wanted to understand neural networks, not just how to use them, but how they actually work. I understood the basics, but I never really got an intuitive feel for backpropagation, and hidden layers stayed more mysterious than clear. There are plenty of great resources out there, but one in particular stood out. Sebastian Legge's How to Create a Neural Network and Train It to Identify Doodles. In his video, he builds a neural network from scratch, tweaks weights and biases, gets it learning, and trains it to classify fruits as safe or poisonous. He then moves on to recognizing handwritten digits and does indeed train it to identify doodles. Please give it a watch. I've linked it in the description. Now, the only way to know it is to do it. We'll build ours entirely in the browser using the Canvas element and standard web APIs. No libraries, no third-party code, no classes either. Instead, we'll take a more functional approach. Check out the source code linked below and follow along commit by commit. We'll be AI mycologists, classifying mushrooms based on two simple features, x and y coordinates on a grid. From there, we'll scale up to recognizing handwritten digits with the MNIST dataset. In the browser, dynamic visuals usually rely on the canvas element. What you're seeing here is a canvas element rendered in the browser. It's 500 by 500 pixels, and each pixel is colored based on its coordinates. We're using the 2D canvas context. That's the built-in object that lets us draw shapes, images, and manipulate pixels directly in the browser. We've also set the intrinsic size of the canvas to 500 pixels by 500 pixels. That's its actual resolution. Here's where we grab the raw pixel data, and the function setPixel writes changes to this image data object. It's just a big array that holds the red, green, blue, and alpha values for every pixel. For every coordinate in the canvas, we pass it into a function that computes what color it should be. Once we hooked up our neural network, we'll run each coordinate through the network so it can predict a class or outcome at that point. We call setPixel to write the color values into the image data object, and finally, to actually apply all those changes onto the canvas, we call putImageData. Here you can see we've centered the coordinates and added some axes. So we've refactored things a bit, and we have this function updateUI, which calls draw. That's where we actually render to the canvas. In draw, you can see how we're interacting with the canvas. One of the first things we do is shift the coordinates so that 0, 0 is at the center of the canvas. We've also got some helper functions here to draw axes and dots. We've updated the UI to display the coordinates of the point currently being hovered over. By clicking, you can select a location to keep it highlighted. So we've added some DOM elements on the page, and we're also keeping a few state variables here. We're passing the current position into our draw function, and we're calling updateCoords, which just displays the coordinates on the page. Really all we've done here is hook up a bunch of event listeners, and those ultimately trigger updateCoords. Here we've normalized the coordinates. The x and y values range from -1 to 1. Normalization is important in machine learning because it keeps input values within a consistent range. This helps the model learn more efficiently by preventing any one feature from dominating due to scale. We've added a new state variable, and we're using it to help initialize the canvas. We also have some helper functions to handle the normalization for us. It's now time to introduce our neural network. A neural network is a stack of layers where data flows from the input layer through 0 or more hidden layers to the output layer, which makes predictions about the input. In a fully connected network like we have here, each neuron receives inputs from every node in the previous layer. Each input is multiplied by a corresponding weight, and the results are summed along with a bias. This sum is then passed through an activation function, which determines the neuron's final output. Note that only the hidden and output layers require weights and biases. The input layer simply holds the input values. With the right weights and biases, a neural network with just a single hidden layer can approximate any function. This is confirmed by the standard universal approximation theorem, which states that a neural network with a single hidden layer can approximate any continuous function given enough neurons and an appropriate activation function. It's like building a smooth curve out of lots of little straight segments, or constructing any shape from simple Lego bricks. Here's our first look at a network. We have an input layer, which right now is made up of empty objects. Then we have a hidden layer and an output layer. The number of weights for each node matches the size of the previous layer. All the weights are set to random values, and the biases are initialized to 0. We've defined our layer sizes and we're passing them into init network. This is all we need to do to generate our network, which we're logging out here. And you can see what's happening. We loop through each layer size. If it's the input layer, we just create empty objects. Otherwise, we initialize the nodes with weights and biases. The weights are set using something called Xavier initialization. It's still random, but the range is based on the size of the previous layer. And importantly, the number of weights for each node is equal to the size of that previous layer. Here we have an input we're feeding forward through our network. Each node has a new property called act, short for activation, which is its output value. And the activations from the last layer is the network's output. Here we're calling the function forward pass with these coordinates. What does forward pass do? First, it takes the input and stores the activation in the first layer. Then, for every node in the rest of the network, we loop through and compute its weighted sum. You can see all that happening here. And finally, we set the activation for each node using this activation function. Right now, the function just returns the value itself. One thing to note, we're using plain for loops here. Functions like map or reduce would definitely be more readable. But we're going with for loops because they're just a lot faster. And when it comes to serious number crunching, like what we'll be doing in this network, that performance difference really matters. Here we're looking at the output layer's activations. The way the network makes a prediction is by finding the highest value. The index of that maximum value is the predicted class. So index 0 means safe, index 1 is poisonous, and index 2 is our third class, the kind you might stumble upon deep in the forest, magical mushrooms. Now we're passing our coordinate through the compute output function, which passes the input forward through the network and returns the final activations. We run those through an argmax function. That just means we're grabbing the index of the highest value. Once we have that index, we use it to look up the corresponding entry in our mushroom info array. This is what our network looks like, drawn on the canvas. Every pixel is passed through the network and assigned a color based on its predicted class. For now, our network will only have two outputs, one for safe and one for poisonous. So here we have initialized our network. And what we're going to do is pass it into the draw function. Inside draw, for every single pixel, we run its coordinates through the network to compute the output. Based on that prediction, we assign a color. Even though we have two output nodes, we really only need one, because this is a binary classifier. If this equation is true, we classify the output as safe. Rearranging, it becomes the equation of a half-plane, which is why you're seeing a straight line boundary in the canvas. We've added this prediction UI, and the idea is, whenever we hover over a point, you can see both the input and the network's output. Right now, I'm hovering over a poisonous area. But if I cross over here, you'll see safe becomes the highest value. I can also click to lock in a point and leave it there for reference. I'll leave it to you to check out the details in this prediction.js file. But here we build the prediction UI when everything is initialized. And whenever the coordinates are updated, we call the render prediction function, which takes care of displaying everything we need to see. Here are network controls for our output nodes. This one is the safe node, and this one is poisonous. And what you're seeing here are their weights and biases. We can adjust these values to see how they affect the network's predictions. You'll notice the decision boundary shifts as things change. For example, I can pick a point over here, and when I adjust the safe node, only the safe output is affected. Same goes for the poisonous node. You can see how it responds in real time. I'll leave it to you to explore the details, but when we initialize the UI, we call this function buildControllsUI, passing in the network and a callback function onParamChange. That sets up the controls, and whenever one of them is changed, it triggers onParamChange, passing along info about which node and which weight or bias was updated. From there, we call setParam, and looking at that function, you'll see it directly mutates the weight or bias in the network. After that, we just refresh the UI to reflect the change. We need some data. We're playing with the weights and biases to see how the predictions change. There you go. That's looking pretty good. So here we have some training data, and we're passing it to our draw function to render it onto the canvas. So what is training data? It's just an array of points. These are our safe points, and these are our poisonous ones. Each point comes with a label, which is one hot encoded, meaning it maps to an index in our mushroom info array. When we call draw, we loop through the training data and simply draw each point using its input coordinates and the corresponding color from the array. We've added a little drop-down here that lets you select different sets of training points. Here's a very simple one, with just 2 points to start with. Here we're importing multiple datasets, and we've added this dataset selector, which you can see here. We've also introduced a few new state variables to keep track of the selected dataset and related info. We populate the selector and have factored most of the initialization code into a function called resetUI. This function runs both initially and whenever the selected dataset changes. It resets the interface based on the new data. We now have an accuracy metric showing up. It's just counting how many predictions the network gets right. Let's see what happens if I tweak this. Okay, that's great. We've added a new DOM element to show accuracy, and in Update UI, we're calling a function called calcmetrics. We pass in the network and the data, and it tells us how many predictions are correct. Inside calcmetrics, all we're doing is looping through the data, computing the network's output for each point, and checking if the predicted class, the argmax of the output, matches the label. It's all well and good to manually adjust these weights and biases, but the whole point is to get the network to learn and train itself. Now we're going to find out how we can make that happen. Let's say we have 2 labeled training points, one labeled safe, the other poisonous. When we pass them through the network, we want the correct output. Safe input should have the first node light up more than the second, and vice versa for poisonous input. But what if that's not happening? The network is getting the safe one right, but the poisonous one wrong. So how do we help it learn? The first step is to assign a target, an actual output that each node should aim for. 0 and 1 work just fine. The exact numbers can vary, but as long as we're consistent, the network has something to aim for, and that's the key. Comparing the node's current output to the target and squaring the difference gives us a number called the cost. We'll compute the cost for each node and sum them up to get the cost for that input. The average cost across all training examples gives the overall cost of the network. And the goal is simple: minimize that cost. To do that, we can use a method called finite differences. You pick a single weight, nudge it slightly, and see how the cost changes. For the safe input, nudging the weight brings the output closer to the target. The cost goes down. We note how the cost changed relative to the nudge. That's the gradient. Specifically, the gradient of the cost with respect to this weight for this input. For the poisonous input, the same nudge brings the output further from the target, so its cost increases. It also increases at a larger rate. When we average the gradients for both inputs, we get the total gradient for this weight. Since the overall cost would go up if we kept moving in this direction, that tells us we need to move the weight in the opposite direction to bring the cost down. That might mean the cost for the safe input goes up a little, but the total cost goes down, so it's progress. We write it like this. Technically, we should use the partial derivative symbol, but we'll keep things simple. We repeat this process for all the weights and biases. We often write the gradient of the cost like this. It just means, here's how the cost is changing, depending on all the weights. Now we know which direction each weight should move to reduce the cost. But how far should we move in that direction? And couldn't updating one weight interfere with another? It could. That's why we need to make sure the steps are smooth and steady. This is controlled by a constant called the learning rate, which scales the step size. Once we have the gradients and a learning rate, we apply the update. Every weight and bias gets adjusted in the direction that lowers the cost, ultimately sending the outputs closer to their targets. Repeat that process. Estimate the gradient, take a small step, update the weights, and the network learns. We're displaying the total cost, and the learning rate is set to 0.1. Watch what happens as we take a single training step. The cost goes down. Now let's take a look at this point. The network should learn to predict it as poisonous, but after another step, the safe output is actually increasing instead of decreasing. But that's okay, because the cost is still going down. We keep hitting step, and you can see the cost continues its descent, and the output slowly creeps towards its target. Now, if we switch to our line example and hit Learn, you can see the network quickly locks in. In fact, the network can learn to separate any linearly separable dataset. Even a model like this, with no hidden layers and no activation function, can still learn to classify it perfectly. That's the principle behind the perceptron convergence theorem, which guarantees perfect classification for linearly separable data using a simple linear model. As the model learns, you can see things are starting to slow down. The gradients have dropped to 0, and this point here still doesn't quite reach its target. That's because the activation is just a raw weighted sum. But that's okay. As long as we can cleanly separate the classes, the network will still reach 100% accuracy. Let's take a look at the learn rate. If we lower the learning rate, you'll see it takes a bit longer. If we bump it up a bit, things will go a little faster. But if we go too far, something like 0.8, we start to see problems. That's right on the edge of being too big. The steps are so large that it can overshoot the target. You can see the cost actually goes up instead of down. And if we crank it even higher, well, forget it. We've added the cost display here, along with a couple of new buttons. Inside Update UI, we're now also pulling the cost from calc metrics. As the function goes through the training data, we add up the cost. Note we've renamed label to target. It calculates the cost for each output node and then takes the average across all the training points. When the step button is clicked, we call this new learn function, passing in the network, the dataset, and the learning rate. Clicking the learn button ultimately does the same thing. So what does learn do? First, it calls compute gradients, then apply gradients. In compute gradients, we start by calculating the original cost. Then we apply a small nudge to each weight and bias, one at a time, and for each nudge, we recalculate the cost. By comparing the new cost to the original, we estimate the gradient. We store these in new properties on each node, grad W for the weights and grad B for the biases. Once we built up all the gradients, we call apply gradients. That just loops through each node and adjusts its weight and biases based on the gradients we just calculated. Now we've entered a whole new world, a magical one, because now there's a third output, a third class. Not totally sure what will happen if I move these around, but each output controls a different class. When the data is linearly separable, even with 3 outputs, as long as these shapes are all convex, this kind of network can still reach 100% accuracy. But once we try something curvy, things break down. It can't capture the shape of the data because it's limited to straight-line decisions. We need to increase the complexity of our network. We can't add more inputs, and we can't change the outputs. The only way to grow the network is by adding hidden layers. Hidden layers are powerful. They let the network combine a bunch of small, simple decisions and piece them together to form more complex patterns. But here's the catch. Even with the hidden layer, the network still isn't working, and that's because we haven't added any non-linear activation functions. Without that, we're just stacking more linear pieces on top of each other, and the result is still just a linear function. To model more complex shapes, we'll need to go one step further and introduce non-linearity. An activation function like sigmoid is useful for 2 main reasons. First, it squashes values. No matter how positive or negative the input is, the output always stays between 0 and 1. Second, it adds non-linearity, which is crucial. Without it, even a deep network would still just behave like one big linear function. And once you have non-linearity, something powerful becomes possible. The universal approximation theorem states that a network with just one hidden layer and a nonlinear activation like sigmoid can approximate any function as long as it has enough neurons. Each neuron contributes a small piece, like a bump or a slope, and when you combine enough of them, they can model incredibly complex shapes. It's like building a smooth curve out of lots of little straight segments, or constructing any shape from simple Lego bricks. And in theory, even something as complex as GPT is built on top of this same idea. Here, we're trying to model something a little more complex, and you can see the network handles it just fine. I've also added a few extra details to the UI. You can now see the frames per second, the step time, and a resolution setting. Frames per second tells you how fast the canvas is updating. Step time, on the other hand, measures how long it takes to process the entire training set during each learning step. Right now, we're running at a resolution of 500 by 500 pixels, which takes a bit of time to render. If we reduce the resolution, you'll see the FPS go up. There's also a blended button. When that's enabled, it removes the training points and just shows the raw network output across the canvas. For example, this yellow region here means both the magical and the poisonous outputs are high at the same time. Now let's say we had 100 nodes in our hidden layer. Here we see it's taking about 1 second per step. For every single weight in the network, we run the entire training set to see how a small change affects the cost. So if we have thousands of weights and hundreds of training points, that means thousands of full passes through the data, one for each weight. The total time grows with both the number of weights and the size of the dataset, and that adds up fast. As we add more nodes and more weights, it only gets worse from here. This is exactly why we need something like backpropagation. It's a much more efficient way to compute all the gradients in one pass, instead of one weight at a time. We start by looking at the output layer. After all, this is backpropagation. It's called that for a reason. We work backwards from the output to figure out how to adjust the weights. Here's a training example labeled safe. We feed it forward through the network. We're just looking at the safe output node here, and compute the cost. Our goal is to reduce that cost. So how should each weight and bias change? Let's focus on just one weight. How does changing this weight affect the cost? It affects the weighted sum, which affects the activation, which affects the cost. Let's break that down. How does the sum change when we adjust the weight? It's a simple equation. We're only changing this one weight, so everything else stays constant. The sum changes in direct proportion to the input. If the input is 0, changing the weight has no effect. For us, the input is negative 0.40, so the sum changes by negative 0.40 per unit change in the weight. Next, how does the activation change as the sum changes? That depends on the slope of the activation function at that sum. In other words, its derivative. If the sum is very positive or very negative, the slope is near 0, so the activation barely changes. It'll always be a positive number. It's at its max at 0, which is 0.25. For us, it's 0.22. Finally, how does the cost change as the activation changes? That's just the derivative of the node cost function. If the cost is close to 0, the derivative is also near 0. For us, it's negative 0.66. Negative, because increasing the activation lowers the cost for this node. And thanks to the chain rule from calculus, the gradient for this weight at this input is just the product of these three values. How the cost changes with the activation, how the activation changes with the sum, and how the sum changes with the weight. Doing the same for the next weight, we see that the cost and activation derivatives are the same for every weight and bias in this output node. So we'll store their product, and we'll call it the node gradient, and multiply it by the input to quickly get the gradient for each weight in this output node. For the bias, we use an input of 1. We do this for all the weights in each output node, and for every training example, and then average the results. This gives us our gradient for the output layer. The best part? We only need to pass each training point through the network once per step, instead of once per weight, like we did with finite differences. Let's check out the implementation. We've moved the learn function to its own file, and you can also see we've defined our activation and cost derivatives here. The structure is similar. It starts by calling clear. We'll get to that in just a moment, but then it calls compute gradients and apply gradients. In compute gradients, we go through the entire dataset. For each input, we run a forward pass. Then, for every node in the output layer, we compute how the cost changes as the activation changes, and how the activation changes as the sum changes. We multiply those two together to get the node gradient, which we then store as a property on the node. To get the weight gradients, we multiply the node gradient by the activation from the previous layer, and accumulate that across all training points. When we call apply gradients, it's almost the same as before, except now we're applying the average of those accumulated gradients, so we divide by the number of training points. And that's why we start by calling clear, to reset the gradients to 0 before we begin. Now let's look at how to apply backpropagation to the hidden layers. Here's a poisonous example. We feed it forward through the network and get an output. Each output node has an associated cost. We add them up to get the total cost for this example. Our goal is to reduce that cost, which means finding the gradient for every weight and bias. It looks complicated, but as you'll see, it's easier than it looks. The key is that we start at the output layer. We know each node's sum and activation, which means we can calculate the node's gradient, and then multiply it by each weight's input, which is just the activation from the previous layer. This gives us the gradients for all the weights and biases in the output layer. Now we'll take a step back and look at the weights in the hidden layer. What happens if I were to change a weight here? We know that changing the weight changes the sum. Changing the sum changes the activation. We know this one too. But what happens when the activation changes? The cost from every output node changes. What if there were 100? Let's just focus on this one. How can we tell what changing the activation will do to the cost of the poisonous node? We'll use the chain rule and see what happens. Changing the input changes the node's sum. Since we're only changing this one input and holding everything else constant, the sum will change in direct proportion to the weight. If the weight were 0, changing this activation wouldn't affect the output at all. So this value is the connected weight. Next, as the sum changes, the output activation changes, which changes the cost. This product we've already computed though. It's the gradient for the output node. Thanks to the chain rule, we just multiply these pieces together to find out how the cost of the poisonous node changes as the activation changes. So what about the other output nodes? Same process. Each connection gives us a similar piece, the connecting weight in the next layer, multiplied by that node's gradient. We sum them up to get our result, how the total cost changes with this activation. We have the cost gradient for this weight. Doing this again for the next weight, these are the same two values, which is the node gradient for this node. We'll store it to quickly determine the gradients for all the weights in the node. We'll do this for all the nodes in the layer. And if there were more hidden layers, then we keep going backwards through the network, layer by layer, repeating this process. Eventually, we'll hit every single weight and get its gradient. We do this for all training examples and use their average. Here's the implementation. For every hidden layer, and for every node in that layer, we calculate how the cost changes as the activation of that node changes. To do that, we loop through all the nodes in the next layer and sum the product of each node's gradient and the weight connecting it back to the current node. This gives us how much the cost changes in response to changes in this node's activation. Once we have that value, we can compute the node gradient for the current node, and from there, it's business as usual to calculate the weight gradients, just like we did in the output layer. Here we have a network with two hidden layers. As training starts, you can see with backpropagation, each step takes about 0.8 milliseconds. But when I switch to finite difference, that jumps to around 18. The real impact shows up as the network gets bigger. Let's bump the hidden layer size to 100. The step time with backpropagation is around 7 milliseconds. With finite differences, like we saw earlier, it shoots past a full second. Backpropagation is what makes training deep networks actually possible at scale. Without it, this kind of learning would be far too slow to be usable. As AI mycologists, we've been working with just two features, the x and y coordinates. But what about something more complex, like handwritten digits? That's where the MNIST dataset comes in. Each data point is a 28 by 28 pixel image, giving us 784 features, one for each pixel, along with a label for the correct digit. We'll train our network to learn from a whole set of these to make predictions. This should look familiar. It's a data point. We have an input and a target. And here are the 784 values of the input, flattened into a one-dimensional array. Here we're importing the tests, creating a grid by passing in the pixel count, and then drawing the input onto the canvas. In build grid, we create a div element for every pixel. And in draw grid, we take each input value, multiply it by 255, and use that to set the background color. Since these are grayscale images, we use the same value for red, green, and blue, so the pixels just show up in shades of black and white. So we'll initialize a network with 784 inputs and 10 outputs, one for each digit from 0 to 9. Right now, it's predicting this 2 is a 1. In fact, it's predicting everything as a 1. Even when there's no input at all, and the pixels are all 0. But that's expected, because at this point, the network hasn't learned anything yet. Out of these 100 test examples, only 14 are correct. So let's get this thing learning. We'll import our network functions and initialize the network with a hidden layer of 100 neurons in addition to the input and output layers. Ultimately, when we update the grid, we draw the input and then render the prediction by computing the output and updating the UI. What you're seeing here is the accuracy and cost for a single batch of 300 samples run through the network. Let's train on this batch and see what happens. I'm speeding things up here, but after training, you can see it reaches 97% accuracy. But that's only on the data it just saw. If we look at the test accuracy, which is based on 100 samples the network hasn't trained on, it's only 52%. The high accuracy on the training batch is because the network has overfit. It's memorized that one batch. Now, let's reset and train on the full dataset, 200 batches, or 60,000 samples total. I've sped things up here, but after a few minutes, we're around 79% accuracy. And it's learned to make the correct prediction for this 5. I've trained a network to about 92% accuracy, and going through the test set, things are looking pretty good. Most predictions are correct. This one isn't though, although to be fair, it's kind of hard to tell that it's a 2. And when the input is completely empty, just zeros, it still predicts a 1. But the real fun comes from trying our own input. I've updated the code so we can draw directly on the grid. Following what Sebastian did in his video, we can sketch out digits and see how the network responds. So here's a 1, a 2, a 3. Can actually see as I start drawing the 5, it already has a sense of what it is. We got 6, 7. Here for 8, if I go slowly, it thinks it's a 5 or a 3. And here it thinks it's a 1. Finally, as we close the shape, it locks in on an 8. Here's a 9, which I got wrong. I've been told 9s are tricky. And finally, 0. So that's it. We built a neural network in the browser, trained it on mushrooms, scaled it up to digits, and I feel like I finally understand how backpropagation works and what the hidden layers are doing. There's still so much more to learn, and I hope this helped make some of it a little clearer. Please find the source code and a link to the app in the description. With a huge thanks to Sebastian for the inspiration, see you next time.